Hello, algebra students, and welcome to your lesson on solving systems by substitution. Our objective for this lesson is talking about how you can use substitution to solve systems of linear equations. Before we go any further, I know we were just getting off of an extra long weekend since there was no school on Monday, so I just wanted to take a second to pause and reflect on what we've already learned about systems and solving systems. In our last lesson, we learned what a system is, and we learned one strategy or method you could use to solve systems. Take a minute, pause the video, and kind of reflect on what you remember. Well, when it comes to what a system is, we learned a system looks like two equations. It's two different equations representing two different constraints in the system. And those two equations are using the same variables because they're talking about the same unknown. When it comes to finding the solution for a system of equations, the method we had learned in the last lesson was how you can use graphing to solve systems. Specifically, we can graph those two equations, see what that graph looks like, and then find that point of intersection. That point of intersection is the solution point because it's going to be the point that satisfies both of the equations and both of the constraints. We were lucky enough when we were doing that lesson to be using a graphing calculator to help us with the graphing, but we are not always going to have access in life to a graphing calculator. And so when it comes to not having graphing as a tool we can use, there are other methods you can use to solve systems of equations algebraically. And we are in an algebra class after all. So that's what these next couple lessons are going to be looking at. The method we're going to be using today is substitution. So instead of a graph, how you could solve these systems using a different way. As our warm-up, we've got the question, is it a match? Below, we are given a graph of two equations in a system. Remember, systems are two equations, so if there's two equations, that's why I've got two lines I'm looking at here. And the question is for us to determine if each of these systems below could be represented by the graphs. And as always, we will be prepared to explain how we know. Before we start trying to decide if these four systems down here represent this graph, I just want to take a moment to pause and talk about that blue line right there. That line is a vertical line. We've spent a lot of time looking at lines like these diagonal lines, but we haven't seen a vertical line in a while. I don't think since pre-algebra. When you are looking at this vertical line here, remember that line is crossing through a ton of different points. There are so many points on that blue line. What do all of those points have in common? Take a moment, pause the video, and think about that now. What do all those points have in common? Well, if I went to make a table of values for this line here, notice I can't do that because we're not given any numbers. But what I would see in that table is that all of those green points I marked, they have the same x coordinate. That number in that x column would be the same for every single one of them. The y value would be different because they're all at different heights. But if I come down to that x-axis, they're all at the same number on our x-axis. So we would see that x value is the same for every single point, no matter what y is. There's something else you know about that x value. We might not see a number there, but you know something about it. What do you know about that number? We know it's a positive number. It's on the right side of our zero or our origin, so I know that number right there in that column would be positive. All of the y's would be different, but it would have a positive value for x. Now that we've talked through that a little bit, I want you to go ahead and try this matching activity here. Could each of these systems represent this set of two equations? And I'll erase all my little dots there. So could those two equations in each of these systems represent the two equations we're looking at? Go ahead, pause the video and decide now. All right. There are a lot of strategies you can use as you're trying to identify if this system if this graph here matches with these systems. For example, as we look at that diagonal line there, I know that line must have a negative slope. When the equations are in slope-intercept form, so y equals mx plus b. If I see a negative slope, like this one here, that means this equation could possibly match up with this. But something like in this last one here, that slope is a positive 2. That would mean that line would be going up and not down. So I could say, well, this last one here does not match that system specifically for that reason, because that first equation has a positive slope, but the equation in our graph has a negative slope. That right there is enough information for me to know that those don't match. Similarly to that table we were talking about at the beginning, when I look at this first system right here, I notice that second equation says x equals negative 5. Think about what that would look like in a table. It means that if x equals negative 5, it doesn't matter what number you put in the y column, x would be negative 5. Doesn't matter what you put in that y column, x equals negative 5. This is telling us that all of those points would have that negative 5 as their x value in common. Similar to this line here, but if x is negative 5, that's on the left side of our origin, and I don't see a line over there. So I know this equation here does not match my system, because that would be a line going through negative 5 on our x-axis. That would be a vertical line over here. That leaves me these last two equations here. This equation here, we already noticed has a negative slope. This other equation here with both x and y is not in slope-intercept form, but if you, in attempts to this matching activity, rearranged it, you'll see that one has a negative slope, so that doesn't help me at all. So we're really going to focus in on these two equations here. This equation says y equals negative 1, kind of like what we were doing before, except reverse. If the equation is y equals negative 1, that tells me it doesn't matter what value I put for x, that y value will always be negative 1. Now, when you're thinking about what type of line this represents, it says it doesn't matter where I go on my x-axis, that y-coordinate would be negative 1. Doesn't matter where I'm going on my x, every single time I would be going down to negative 1. Doesn't matter if I go over to 1, down to negative 1. If I go to 2 on x, I'm going down to negative 1. If I go to 5 on x, I'm going down to negative 1. That right there describes a horizontal line, like that. That would be crossing through your y-axis at negative 1. That is going to be the reason why this one here does not match up with our graph. That leaves me with this right here. If I were to rearrange that first equation and solve for x, that gives me x equals 8 over 3, which if you did divide out, that's 2.67. That is that vertical line right here, and it could be going through 2.67. We don't know what the numbers are like on that x-axis. And if you rearranged that second equation and solved for y, you're seeing that y equals negative 3x plus 15. We had mentioned earlier that black line there has a negative slope, which this equation does, has a positive y-intercept at 15, which this equation does. So this third system here could match this graph. This was a great opportunity for us to warm up, start matching some graphs to systems, and gets us ready for the second part here. Now that we've kind of thought through what these systems look like, the second part, we're going to actually look at solving these 4 systems. So it says in the second part, here are 4 systems of equations you saw earlier. Solve each system, then check your solutions by substituting them into the original equations to see if the equations are true. Let's focus in on how we would solve each of these systems first. Remember, we had talked earlier in the last lesson about how one strategy you can use to solve systems is by graphing. I could graph each pair of these equations and find that intersection point. That's one method we could use. But as we mentioned earlier, you don't always have access to a graphing calculator, so instead, we want to know how to solve these algebraically. One method you can use is, the title of this notes, is substitution. As I'm looking at these 2 equations here, I know my answer is going to be a pair of numbers. I'm going to have x equals something and y equals something. As I'm looking at this pair of numbers, I already see what x equals. I see x equals negative 5. Just by making that observation, I've got half my answer. I've got x equals negative 5. I need to know what y equals. how could I use the fact that I already know x to help me figure out y? Well, if x equals -5, I can use that information in that first equation. I can take that x equals -5 and substitute it into that other equation for x. When you substitute, remember that means you're taking out the variable and replacing it with the value. So if I substitute that, it's going to say -5 plus 2y equals 8. That helps me out because now I've got an equation with only one variable, and I can solve this equation for y. I can figure out what value y is. In order to do that, I'm going to start with my constant and add 5 on both sides. I'm adding 5 because that is a -5, and -5 plus 5 gives me 0, so that eliminates my 5. That leaves me with 2y equals 13. My last step, because 2y means 2 times y, I'm doing the opposite, and I'm going to divide both sides by 2, and that leaves me with y equals 13 halves, or we can say 6.5. So I've got my final answer. X is the number -5, and y is the number 6.5. It's that combination of values that satisfies both of these constraints, that satisfies both of those equations. Now they mention up here in the directions, solve each system, then check your solutions by substituting them into the original equations to see if the equations are true. Before we started looking at systems of equations, we talked about how you can check to see if something's a solution, and it involves a lot of substitution. The same thing is true here. If I wanted to check to see if this combination of numbers is a solution for both of these equations, it looks like me substituting my solutions into the original equations, the directions say, and make sure it gives me something that's true. When I go to check that first equation, the x plus 2y, instead of x, I'm writing -5 plus 2. Instead of y, I'm writing times 6.5 equals 8. And I want to check to make sure that's true. When we do that math, we get -5 plus 13 equals 8. And -5 plus 13 does in fact equal 8. That tells me it's true. It satisfies that equation. When I go to check that second equation, which says x equals -5, well, when I substitute it, it says -5 equals -5. That one's easy. It requires no math. That one's also true. So I see this pair of numbers satisfies both of those equations. This is an example of how you can use substitution to help you solve these algebraically. I found that intersection point without ever looking at a graph. Now that we've seen this example, I'm going to have you come over to system B. Go ahead, try solving that system of equations using substitution. Alrighty. For this second one here, you should have substituted y equals -1 into the other equation. When you do that, it ends up looking like -1 equals -7x plus 13. When you go to solve that equation, you get that x equals 2. And so you get that final answer of x equals 2 and y equals -1. If you were to substitute that into your equation here and your second equation here, similar to this, you would see that that combination of values makes both of these equations true. The fun continues down here with another 2 equations. If I look at system C, I see the equations 3x equals 8 and 3x plus y equals 15. I'm going to have you go ahead, pause the video, and try to solve system C. What ideas did you come up for system C? Well, system C is a little different from the first 2, because in the first 2, notice that I knew the value of x was -5. I knew the value of y was -1. But in this system here, I don't see x equals and I don't see y equals. So starting off, I don't know the values of either of those variables. What we do know is this first equation here only has one variable in it, and it says 3x equals 8. there's two strategies you can use as far as substituting goes to solve the system. I'm going to flip us over here. So the first thing we could do as our first strategy, I'm going to hide all the work, is find the value of x and substitute that into the equation. So like the other one said x equals something and y equals something, let's use this equation, the 3x equals 8, solve that equation for x, and then substitute into the other equation. If I wanted to do that, I'm starting with that 3x equals 8. Box, go away. When you solve that by dividing by 3 on both sides, you get x equals 8/3. And now that we know what x is, now we could substitute into that original equation. That was the second equation, the 3x plus y equals 15. I could substitute x for 8/3, like so. When you multiply the 3 by 8/3, it's really nice. Those 3's cancel out, so you're left with 8. And then when we solve the equation 8 plus y equals 15, you end up getting y equals 7. So we get the solution for this system that way. We get x equals 8/3 and y equals 7. Now, because of the way this system here looks, there's another strategy we could use. I notice at the top it's telling me 3x equals 8. And then in the second equation, it says 3x again. So instead of solving for x first, another strategy you could use is just start off by saying, well, if 3x equals 8, then I'm going to substitute 8 for 3x. I'm going to take out the 3x and replace it with 8. If you use that strategy, notice here, let me take away my little block. Notice here they've taken out that 3x and we're replacing it with 8. And then by doing that, you get 8 plus y equals 15. Subtract 8 on both sides and you get that final answer of 7. That is a different strategy you could use to solve this system. Comparing the work of these two, you might notice, well, yeah, that second one was so much quicker than the first one. Remember, for the second one, you would still need to solve for x and get that 8/3. But the second way, the value in it is you did get to avoid that fraction there and having to do the math with fractions. The only reason we were able to do that, though, is because that system used 3x again. If instead it said 4x plus y equals 15, what would we have to do there? Well, if it said 4x, we wouldn't be able to replace the 8 for 3x, so I would have to solve for x first, find the value for x, and then substitute. D is similar in that there are multiple ways you could solve D. Go ahead, pause the video now, and try solving system D. So for system D, there's two ways you can go about it. I think the way I'm guessing more of you solved it is by looking at that second equation, see how it only has one variable in it? We can solve that second equation for y. Looking at 4 plus y equals 12, you could subtract 4 on both sides and get y equals 8. That helps us because now that we know y equals 8, we could use that in that first equation, the y equals 2x minus 7. Substitute 8 for y, you get 8 equals 2x minus 7. And then when we go to solve that equation, add 7 on both sides, divide by 2 on both sides, and you are left with the equation 7.5 equals x. So we can get that combination of values that way. X is 7.5 and y is 8. The other way you could do this problem. Now, we mentioned earlier we didn't know looking at the system what value y was, but we do know what y equals. It tells us in system D, y equals 2x minus 7. That is what y equals. Just like you can substitute a value, like -1, into another equation, you can also substitute an expression. And that's what 2x minus 7 is an expression. If I know y equals 2x minus 7, anywhere I see y in the other equation, I can substitute 2x minus 7. So if y equals this, I can take this, the 2x minus 7, and replace y with that. When I do that, that 4 is still there, the plus sign is still there, but remember I'm taking out the y and I'm putting what y equals, which in this case is 2x minus 7. You can write here 2x minus 7. Sometimes you'll see parentheses around it because it's more than one term. So just showing, hey, I substituted this group here for y. In this case, it's not necessary. They both mean the same thing, so it's up to you. But don't forget about those parentheses because they might be important later on. By doing that, it gives us this equation here. I could combine like terms. There's many ways you could solve this equation here. Let me recognize that first. I'm going to start by taking that 4 minus 7, combine those terms and get negative 3 plus 2x equals 12. After that, I'm going to get rid of my constant. Let's add 3 on both sides because negative 3 plus 3 gives us 0. That leaves me with 2x equals 12 plus 3, which is 15. I can then divide both sides by 2. And that leaves me with, drum roll please, x equals 7.5. Notice that's the same thing we got over here. Both of these strategies lead you to the same answer. So I want to recognize that. But it's good to know that when it comes to systems, you can always use more than one strategy. And you probably will see more than one strategy. Notice all 4 of these systems here had something in common. All of them had an equation with only one variable. That first one was just x. Second one was just y. This third one here, that top equation had x. We had to solve for x, but it still only had x. This last one here, again, like we had to solve for it, but it only had y. But more often than not, that's not what you see. Lots of times we see 2 equations that have both x and y in it, like these ones below here. Looking at this first one, we've got the system 5x minus 2y equals 26, and y plus 4 equals x. When I look at that system, the first thing I realize is, I'm not going to be able to do what we were doing earlier, which was finding the value of one of those variables and then substituting that value into the other one. Here, nowhere do I see like y equals a number, x equals a number. So instead, what we're going to need to do is similar to what we ended up doing in this last one here. I'm going to end up having to substitute an expression with a variable in it. When I look at this first system here, I notice that that second equation tells me what x is. It tells me x equals the y plus 4. I'm just reading it in the reverse order. How could I use that to help me solve the system? Well, if if x equals y plus 4, I can take that y plus 4 and substitute that for x. I can take that y plus 4 and substitute that for x. By doing that, it'll give me an equation that just has y in it that I can solve. When I go to substitute, notice originally it said 5 times x. When I substitute, I don't want to forget about that multiplication. That original equation said multiply whatever x is by 5. When I substitute, I need to show that by saying 5 times y plus 4, like that. That's showing I'm multiplying whatever x was, which was the y plus 4, times 5. Those parentheses are important because you want to show that you're multiplying everything that x equals by 5. After I've substituted my x, I've got that minus 2y equals 26. And now I've got an equation that I can solve for. Go ahead, pause the video now and finish solving that equation. All right. You could start by distributing that 5. When you do that, you get 5y plus 20 minus 2y equals 26. I think the next thing I'm going to do is let me subtract that 5y minus 2y. It gives me 3y plus 20 equals 26. Then I'm going to come in, I'm going to subtract my 20. As I do this, remember, there is more than one way to solve an equation. So you might have gone about this in slightly different steps. Once I divide by that 3, though, that'll give us our final answer. We got y equals 2. Again, you might have solved that equation differently, but as long as you got that y equals 2 as that final solution, you're good to go. Now remember, we're trying to solve the system, which means we need a pair of values. I know what y equals. I don't know what x equals, though. How could I figure out what x equals? Well, I can take my y equals 2, kind of like what we were doing earlier, and substitute that value into an equation to solve for x. Notice I've got two different options. I could substitute that 2 into either of these equations. Do you think it matters? Well, if you're unsure, I encourage you, pause the video and try it in both of them. See what happens. If I substitute 2 for y in that bottom equation, we get 2 plus 4 equals x. That tells me 6 equals x. If you substitute y in that top equation, you get 5. Ooh, where did my text go? You get 5x minus 2 times 2 is 4 equals 26. That gives you 5x equals 30 and x equals 6. So we end up getting the same answer for both. I chose that bottom one because the math looked a little easier, but either way, you end up getting 6 for x. So we've got that combination of values there. This was my example. Go ahead and try the second one here. Okay. I'm going to move us down to these last two examples. When I go to look at this third system here, 2d equals 8f and 18 minus 4f equals 2d. Looking at that, this system is different from these first two. Do you see why? Well, in these first two, we were given a variable. We weren't told what value it was, but in that first one, I was told, well, x equals this. And that one you just completed, you were told p equals 2m plus 10. So we had something to substitute from the get-go. In this one here, I don't have anything. I don't know what d equals, and I don't know what f equals. Kind of like what we had done back up here. Earlier, remember, we didn't know what x equals or what y equaled. So we started off by solving for that variable. That way we were able to substitute. So the same thing down here, the difference is just instead of solving and getting a number, when we solve, we're going to get an expression like y plus 4 or 2m plus 10, something like that. Looking at that first equation there, I noticed there's one step I could do to get d by itself. If I'm given 2d equals 8f, I notice if I were to divide both sides by 2, that's one quick step I could do to get d all by itself. That gives me d equals 4f. After I've got d equals 4f, that is an equivalent equation to the 2d equals 8f. And now it's similar to what you had done earlier. If we know d equals 4f, we can finish solving this system here by substituting 4f for d. If I look at that second equation there, I've got 18 minus 4f equals 2. There's my d. Instead of d, I'm going to write 4f. When I do that, that gives me 18 minus 4f equals 8f. I've got f's on both sides of the equation. I need to move it to one side, so I'm going to add my 4f on both sides. That leaves me with 18 equals 12f. And when I divide both sides by 12, that leaves me with 1.5 equals f. Still not my final answer. I only have f. I also need to know what d is. How could we calculate what d is? We've got a bunch of equations all over the place that you could use. I'm going to use this one right here that says d equals 4f. If d equals 4f and f is 1.5, that means d must equal 4 times 1.5, which means d equals 6. And so we get 6 as our answer there. Now, when it comes to systems and solving systems by substitution, lots of times there is more than one way to go about it. So this was an example of one way you could solve. Notice I started by getting d all by itself so that I could substitute 4f for d. Another strategy you could use for this system here is if 2d equals 8f, notice I see 8f in that I see 2d in that second equation there. I see 2d right here in addition to right here. So instead of solving for d, a different strategy you could use is if 2d equals 8f, I could substitute 8f wherever I see 2d, which means I could replace that 2d with 8f. It means I could substitute in that second equation and say 18 minus 4f equals, instead of 2d, well, 2d is 8f, so it equals 8f. I feel like I'm saying 2d and 8f a lot. If we do that, that gives us that equation there in blue. I could come in and add 4f on both sides. If we do that, that gives us 18 equals 12f, and then divide both sides by 12, and you get that 1.5 equals f. Notice that process was a lot quicker than what we had done earlier because you're cutting out that step of having to get d all by itself first. Both of these strategies, though, are using substitution, and both of them are giving you that same solution at the end. This was my last example. You've got one here for you to try. Again, these substitution system problems have many ways to go about it. See if you can find one strategy you could use to solve the system here. All right, so looking at this system, one strategy we could use is saying, hey, I see z equals 3w minus 2. If z equals 3w minus 2, that means anywhere I see a z, I can replace it with this. So let me do that. Let me replace z there. When we do that, we get w, that's not a w, we get w equals 1/7 times z. Because z is multiple things like that, did you use parentheses? I hope you did. You get 3w minus 2, and then equals 4. What did I mess up? Oh, I'm sorry. It's supposed to be w plus, and I wrote w equals. I was about to do it again. No, I did do it again. W plus 1/7 times our z, which happens to be 3w minus 2, equals 4. When we go to solve this equation for w, I've got w equals, well, I'm going to multiply my 1/7 times 3w. That gives me 3/7 w minus 1/7 times 2 is 2/7 equals 4. What? Oh my gosh. Y'all are probably laughing at me at home. There's the plus sign. Okay. Looking at this equation here, you could keep going with all these fun fractions in there. I'm going to use the strategy of, in order to get rid of that fraction, since the denominator is 7 and it says divided by 7, I can get rid of that by multiplying both sides of our equation by 7. I'm going to multiply this left side by 7. So let me put all of that there. And then I'm going to multiply the right side by 7. That's going to give us an equivalent equation, except it's not going to have fractions. When we multiply both sides by 7, you get 7w plus 3/7 times 7. Those 7s end up canceling out, and it just leaves us with the 3. So we get 3w. Similarly, with the 2/7 times 7, gives us a 2 equals 28. Again, you could have left those fractions there, but I didn't want to. I'm going to come in, I'm going to add 2 on both sides to get rid of my constant. That gives me 10w equals 30. Then I can divide both sides by 10, and that gives me w equals 3. Once I've got w equals 3, I can use substitution again to figure out what z is. I could use the first or the second equation. I'm going to go for the second because you saw I didn't want to do the math with fractions today. So I'm taking that second equation, z equals 3w minus 2. We're substituting w for 3 and not forgetting that equal sign. That gives us z equals 9 minus 2, or z equals 7. So I get that combination of values as w equals 3, z equals 7. There is a lot of systems in this set of notes. Remember, we would always love to see you for tutoring, in person or virtual. If you're having trouble with solving systems, we've got tons of practice on this stuff. So please, please, please reach out to us if you need any extra help on these. This is where we'll stop for this lesson. Thanks so much for watching. Bye.